Hey everyone, and welcome back to another studio review video. So today what we're going to be doing is going over studio number 2, which is going to be our introduction to vector math and also MATLAB. So let's go ahead and jump right into it without any further ado here. So like I said, just what's on the slide here, today we're going to be going over vector math. That's the primary goal. So as I understand it, some of you all have seen vector math before in high school, and some of you haven't. Some of you are in Math 200 or Math 180, and so you're learning or already have learned all of these concepts by now. And some of you aren't. So what we're going to do is we're just going to go over all of this stuff so that everyone's on an equal playing field, and you'll have plenty of opportunities to practice this stuff when we do our statics portion of the course, which will happen in a few weeks. And also on the homework, which was just released today. So that's the main thing we're going to be going over. And then we're also going to introduce this concept of a free body diagram. This isn't a critical thing for this studio, but there is a lot of vectors involved in drawing free body diagrams, and we're going to revisit this concept later. So it will come back, but we're going to touch on it a little bit. And then MATLAB. So we're going to introduce you to this very, very important software called MATLAB that you'll be using for the rest of this class and probably for the rest of your career if you decide to do engineering. So yeah, let's go ahead and jump into the content. So first things first, I'm talking about vectors and vector math. What even does that mean? What is a vector? So before we talk about vectors, we need to introduce scalars. So scalars are what everyone has seen before for sure. Scalars are just numbers, okay? It's just a magnitude. You could have something like distance, speed, mass, temperature, whatever. It doesn't matter. It's just a number. 3, 4, 5, 10, 1,000, all numbers, all scalars, okay? If I say something like 10 miles, that's a scalar. Okay, now a vector is distinct from a scalar in that it has a magnitude component, which the magnitude in itself is a scalar, but it also has a directional component. So I said before 10 miles is a scalar. Well, if I said 10 miles east, now I've created a vector quantity because I have this concept of magnitude, 10 miles, and direction, which is east in this case. Okay, and so we see vectors in a variety of real life situations. Some of them are on the slide, as you can see here: velocity, force, acceleration, displacement, and so on. Okay, so that's kind of what we're going to be introducing today. Okay, but those two terms are very important, and so just keep that in mind, and because we'll be using those throughout the rest of this studio here. Okay, so quick digression into free body diagrams. This isn't what we're going to be focusing on in this studio, but like I say, it is an important concept that we're going to revisit later in the class, and so it's a good thing to introduce now. So basic idea with a free body diagram, right, is I want to represent some object and all of the forces acting upon that object so that I can basically do math and represent that object mathematically, okay? So basically, what you're going to have is you're going to have some object, and then you're going to have a bunch of forces. So as you can see on the slide here, we've got some forces kind of normal to this inclined plane that this block is sitting on, and then we have F3, which is pointing up the plane. That might be some sort of frictional force preventing it from sliding down, and then we've got some sort of force, the gravitational force F1, pulling the object down. So those are very common things that you'll see. And these are all vector quantities, and so that's why we're representing it in this studio. You know, F2, F3, they each have a direction. They're each going to have a magnitude as well. Okay, and then the other thing you want to do is important angles. So you'll see that angle alpha that's represented on the diagram here. So this is that angle of the plane, the inclined plane. Anything like that, any pertinent information, you're going to want to represent that on your FBD. So one thing that I've been told and that I think is good is if you can set aside the problem statement after you've drawn up your FBD and you have all the information that you need to solve that problem represented on your FBD, then you've probably done a pretty good job including all of the relevant information on your free body diagram. Okay, so that's just a quick intro to free body diagrams, and like I said, we'll be coming back to this in about 2 weeks when we do our statics studio. Okay, cool. So now let's get into sort of the heart of the studio, which is the real vector math. So first things first, the first concept that we need to introduce is this idea of coordinate systems. So the first coordinate system that we're going to talk about is Cartesian. So let me write that out here. So we've got Cartesian. And the Cartesian coordinate system is something that you all have used many times. Even if you don't know the name, you know this coordinate system. So this is just your x, y, z, or x, y coordinate system. So basically, we're just going to have something like this kind of sort of basic coordinate system here. So there's y, and here's x here. Okay, so there's our coordinate system, and my vector might look something like this. So there's my vector. And so that vector will have some distance here. Call this distance maybe capital X, and we'll call this distance capital Y. Okay, so this is Cartesian. How do we represent vectors in Cartesian? So we're gonna have these brackets. We use this bracket notation for vectors, and there's another notation that we'll talk about in just a sec here. But a lot of times you'll see this bracket notation for vectors. So we have a bracket, and then we're gonna have our X component, our Y component, and then if we had a Z component, we would include that as well. In this case, we don't. So I'm gonna get rid of that, and we're just gonna leave it as X comma Y, okay? So another format you'll often see is this I hat, J hat, K hat notation. Now I hat, J hat, and K hat are unit vectors. So that's sort of like this mysterious concept that we'll talk about later, but just keep that in mind. I hat, J hat, and K hat are unit vectors. It's really pretty simple, but we'll just explain it in a few slides from now. But just keep that in the back of your mind. So the other way to do this, so we write X I hat plus Y J hat, and then if we had a Z value plus Z K hat. In this case, we don't have a Z value, so I'll just X that out. But that's Cartesian, okay? This is the coordinate system you've all heard of, or maybe not heard of, but you've seen it before, okay? So another common coordinate system you'll see is polar. So I'm gonna erase this Cartesian label here, and let's talk about polar a little bit. So in a polar coordinate system, instead of having X and Y here, we're instead going to have r, which is the magnitude of this vector here, and theta, which is the angle that it's making with the x-axis. Okay, so r is going to be my magnitude, and theta is going to be my directional component. Okay, and so how do we represent this? So polar, let's use our bracket notation. So we're going to have r, comma, theta. And now in 3D, there's another similar coordinate system called spherical coordinates. If you take Math 200 or Math 180, then you'll see that coordinate system and you'll use it. But in this class, we're not going to get into it. It's really not so complicated. There's just another angle because it's in 3 dimensions. Okay, so we'll keep it like this for now. But just remember, this is the magnitude, and this is the angle slash my directional component, right? Okay, so that's that. There's our two coordinate systems. So now the main task here is to figure out, well, how do I move between coordinate systems? How do I convert between Cartesian and polar, or polar to Cartesian, right? So there are a few equations that are important when thinking about this, and we could just write them down, but it's actually really easy to derive them, so let's do that instead. So I'm just going to redraw my little diagram here to make this really clear. So I'll have my vector, and it has some magnitude r. It's got this angle theta, and then we're going to have some distance here. This side is going to be called x, and this side is going to be y. Okay, so we've got all the information we need. So first things first, let's go from Cartesian to polar. Cartesian to polar. Okay, so if we're going from Cartesian to polar, that means that we know x and y, and we want r and theta, okay? So just keep that in mind. So x and y are known. So in this case, we're gonna start off with finding the magnitude. We wanna find r first. You can find whichever first in reality. I'm just gonna start with that. So let's just use the Pythagorean theorem for this. So in this case, we're gonna have x squared plus y squared is equal to the hypotenuse squared, which is r. And so then I take the square root on both sides, and I end up with r is equal to square root of x squared plus y squared. Okay, so there's equation number 1. Okay, so now I've got r, now I just need theta, right? Well, if we look at this here, we have this adjacent side with respect to this angle, and we have this opposite side. So adjacent and opposite are known, so we're going to use tangent for that, okay? So in that case, we're going to have tangent of that angle theta, let me just zoom out here, is equal to opposite over hypotenuse I'm sorry, not opposite over hypotenuse, opposite over adjacent. And that is going to be y over x, okay? And then now I can just solve for theta pretty simply here. So that'll be theta is equal to arctan of y over x. So there's our second equation there for theta. Okay? So now let's go from polar to Cartesian. So polar to Cartesian. So remember now in this case, we have r and we have theta, and we want to find x and y, okay? So just keep that in mind, that's kind of our goal here. Okay, so in this case, let's find x first. So if we want to find x first, x is going to be our adjacent side. We know r, that's our hypotenuse in this case. So let's use cosine, right? So cosine of theta is going to be equal to adjacent over hypotenuse, which is going to be x, because that's the adjacent, over r, which is the hypotenuse. Then I can solve for r, or x rather. So x is going to be r times cosine theta. And then in a very similar way, we can solve for y. So in the case of y, y is my opposite side, so I'm going to use sine. So we're going to have sine theta is equal to opposite over hypotenuse. That's going to be y over x, or y over r. And in that case, we're going to have y is equal to r times sine theta. And there's our other equation. So these are our four main equations that we're going to need to convert between coordinate systems. Okay, cool. So now that we've covered all of that, those are kind of the basics on just coordinate systems and how to go between them. Let's actually talk about vector operations. So that's kind of the main topic that we need to get into when we talk about vector math. So let's get into that. So first things first, we're going to start simple. We're going to talk about addition and subtraction. So in each of these cases, what I'm going to do is I'm going to lay out a general sort of formula that's just variables and symbolic, and then I'm going to give you a quick example. So with vector addition, it's pretty simple here. So all we're doing is, let's say I have some vector a, comma b, comma c, and I add d, comma e, comma f. So all I do in this case is I just add component-wise. So I add the x component to the other x component, so a and d, and then my next component will be b plus e, and then my next component will be c plus f. Okay, so let's just write that out. So we're going to get a plus d, comma b plus e, comma c plus f. Okay, and that's it. So that's addition, and this really takes care of subtraction too, because it's the same deal, but we'll go over that explicitly just to be really sure about that. So let's give a quick example here. So we're going to do this vector 1, comma 2, comma 3, plus 2, comma 4, comma 6. So 1 plus 2, 3, 2 plus 4, 6, and 3 plus 6 is 9. So that'll be our vector, and let's write it in our other format as well. So 3i hat plus 6j hat plus 9k hat. Okay, so there we go. There's our addition example. Okay, so let's go over subtraction now. One other thing I'll point out about addition before I do that though, is that what this will look like physically with the vectors. Let me just draw out this plane here. So let's say I have this vector I'm adding it to this orange vector. So when I add two vectors, what this really does is it's kind of like I'm taking this vector and I'm moving it to the beginning of this orange vector here. And the resultant vector will be this blue vector right here, okay? And so what we can kind of do, so instead of moving this, I'll just copy it. So we'll move that. So what we're really kind of doing, as you can see, is creating this sort of parallelogram shape. So you can kind of see right here, this parallelogram. So you can kind of think of addition like that. Okay, so that's what it looks like physically. We're just kind of moving vectors around. Okay, great. So now subtraction. It's exactly the same as addition, but we'll write it out just to be thorough. So A, B, C, in this case, minus D, E, F. Okay? And in this case, instead of adding each component, we're subtracting. So it's just going to be A minus D, comma B minus E, comma C minus F. And that's all. Okay, so for our example, we'll do the same thing except subtract these two vectors. So 1, 2, 3 minus 2, 4, 6. All right, so in that case, what we'll get is -1, -2, -3. Or we can write it in this I, J, K hat notation. In that case, it'll be -I hat or -1 I hat, -2 J hat, -3 K hat. So hopefully you're kind of getting the hang of these notation differences. Okay, cool. So I mentioned before that I hat, J hat, and K hat are unit vectors, but I never really explained what that meant. So now we're going to actually explain what a unit vector is. So mathematically, a unit vector is just a vector with magnitude 1. That's all it is. It's just a vector that has a magnitude of 1. So in the case of I hat, J hat, and K hat, let's see what these vectors actually look like, because they are vectors. So we're talking about unit vectors now. And we said, okay, unit vectors are just vectors with magnitude of 1. And remember, we know the magnitude formula already because we derived it before. The magnitude formula is just this. It's just R, okay? And perhaps we'll add a plus z squared right here to our complete 3D magnitude formula. But that's all it is. So we've already derived that formula. And so let's look at I hat, J hat, and K hat now. So I hat is actually, if we use the bracket notation, 1, 0, 0. J hat, turns out, is 0, 1, 0. And K hat is 0, 0, 1. So that's what they actually are. And we'll see if we take the magnitude of one of these, so magnitude of I hat, so you'll notice these absolute value bars here that I'm putting around I hat, that just means magnitude. So you can associate those absolute value bars with magnitude. So if I want to compute that, it's just going to be 1 squared plus 0 squared plus 0 squared, all square rooted. And that's going to be 1. So checks out. That's the only requirement for being a unit vector, so that works out. It is a unit vector. And just so we can see how this works a little bit better, let's take this result that we got before and see if this checks out. So let's grab this and move that down here for a minute. And let's plug in each of these definitions for I, J, and K hat. So we're going to have 3 times I hat plus 6 times J hat plus 9 times K hat. And in this case, what we see, if we multiply all of this out, we get back to 3, 6, 9. So look at that. This value is the same as this value. So it checks out. So that's how you can see now explicitly that those two forms are equivalent. So now that's all great. I see how it works mathematically, but what's the point? Why ever use a unit vector? Where will I actually use this? Well, let's say I have a direction, like 1, 2, 3, okay? I have some force going in some direction defined by that vector that I just said, 1, 2, 3. But that force has a magnitude of 50 newtons. Well, how do I represent this situation as a vector quantity? So let me write that out. So I have force of 50 newtons going in direction of this vector. Okay? So now the question is, how do I represent this? As a vector. How do I represent that force as a vector? Okay? So we immediately might just say, okay, well the magnitude is 50 newtons. So 50 newtons times, and I know the direction. So that's my magnitude 50. I know the direction is 1, 2, 3. So there we go. Now we've got a vector that has 50 newtons as its magnitude. It's going in this direction. But unfortunately, that's not exactly what we've just done, because this vector is not a unit vector. It doesn't have a magnitude of 1. So this has a non-zero magnitude, and we've just multiplied that magnitude by 50. So now my resulting force vector here no longer has a magnitude of 50, which is what I wanted to begin with. So what do? We need to normalize this whole thing, this vector, by its magnitude. So we just normalize. So we just divide by the magnitude. So how do we get the magnitude? We use that formula like we just went over. So there we go. Each of the components squared and added together, and then all square rooted. Okay? So now we have something with magnitude 50 going in the direction of the vector that we specified in the problem. So that's where we'll see unit vectors used a lot for this class. Okay? So that's just one example of where this might be useful. Okay? So there we go. So now just to be clear, we'll call this vector, we'll call it f. And notice f is a vector, so I've included this little arrow above it to show that it's a vector. That's just a notation thing. And so we can say that the magnitude of f is 50, which is what we wanted, and its direction is given by this. Okay, and you could multiply all of that out. I'm not going to do that. We'll just leave it in this form for now. But you could multiply this out so that you get like something, some number, like whatever, something in this format. But it's not important for this problem. So we'll just leave it unsimplified. Okay, so that's all. So general form though, just so that we have a concrete final statement here about what a unit vector is and how I get one. So a unit vector is just going to be some vector divided by its own magnitude. And that's it. So this is the formula for how I derive a unit vector from some random vector. And you can see we use that formula right here. So that, what I just circled in red, is my unit vector in this situation. Okay, so next thing we're gonna go over is cross product. So this is gonna be our most complicated mathematical operation. So we're just gonna do it first, and then we'll end with a slightly easier operation, in my opinion anyway, which is gonna be dot product. So first of all, what is cross product? So what a cross product does is it helps us define a plane when we have two lines sitting on said plane. So how does it do that? It gives us a vector perpendicular to the two vectors that I cross. So I cross two vectors, I get a line or a vector perpendicular to those two vectors that I crossed, okay? So that's kind of what it does. Now let's talk about how to actually compute cross product, okay? So let's write this out here, cross product. Okay, so general form, A, B, C, cross, so that is the symbol that we use for cross product. So that's not multiplication, that is cross, D, E, F. Okay, so now there's two methods for computing cross product. I will go over both of them. Feel free to choose your favorite and stick with that. But these are the two main methods that I've seen. There are plenty of other methods, so if you don't like these, or if you have your own that you prefer, feel free to look up stuff or use your own if you already have one. Totally fine, however you want to do it. So this is my favorite method I'm going to do first. So my favorite method is to take this first vector right here and write it out. And then I take the first two elements and I write those out again. I do the same thing with this vector, except I'm going to put that on the bottom. So we're going to write D, E, F, and then we repeat the first two elements just like we did before, okay? Now, starting from the right and moving to the left, I circle groups of 4. So I'm going to circle this group of 4, this group of 4, and this group of 4. And now we're going to actually compute the cross product. So, all in all, what we're going to do is we're going to do B times F minus C times E. So you can see the little cross there. So that's our X component. So put a comma there. And then we're going to do C times D minus A times F. Okay? Last component, A times E minus B times D. Okay, and that's it. So that's how you compute the cross product. It's kind of a strange operation. As you do more and more of this, you'll get used to it. It just takes practice. So the other method that I've seen is this sort of column method. So let me write that out now. So this is method 1. Method 1. And now let's do method 2. So this is not my preferred method, but some people like this better. So once again, we have the same thing. We have A, B, C, crossed with D, E, F. Okay, and we want to compute that. So if that's the case, what we're going to do in this method is we're going to write out I, J, and K. So those are our components. And we're creating this sort of table. So we'll write out the first vector, A, B, C, and the second vector, D, E, F on the bottom, okay? So the setup for this one is a little bit simpler, but the execution is a little bit more complicated. So it's kind of like pick your poison, whichever one you want to do. It's like this setup is a little more complicated, but the computation is straightforward. This one, the setup is really simple, but the computation is a little bit more confusing. So either way though, it just takes practice and you'll get used to it. So with this method, what we're gonna do is we're gonna start out positive. So our first component, we're gonna write this in parentheses, will be positive. That'll be our I component. Then our J hat component will be negative and our K hat component will flip and be positive again. So we're kind of alternating, okay? And now what we do, so we're computing the I component, the X component. So we're gonna block out I, okay? So whichever one we're currently computing, we block that column out. And then we're gonna cross the columns that are left. So we're gonna do B times F minus C times E, okay? And that'll be I hat. Then we're gonna flip and go minus the next set. So let's reset. And now we're gonna cover this J column and we're gonna cross the columns that are left. So we're gonna have A times F minus C times D. And that'll be J hat. Last one, we're going to flip back to positive. Let's reset. So we're going to cover up K this time. So we're going to go A times E minus B times D. Let me move all this over. And that'll be in K hat, okay? So if I scroll all the way out here, hopefully you can see that these two are absolutely equivalent. It's just a different way of computing things, okay? So like I said, pick whichever one is easiest for you to understand. It doesn't matter, you'll get the same result every time, okay? So that is how you actually compute the cross product. There is another very important formula that we need to go over though. So you'll notice just now when we did the cross product, we crossed two vectors. We get a vector perpendicular to the two vectors that we crossed. And notice what I said there, I crossed two vectors and I get a vector. So that's very important. That doesn't always happen with these operations. So in addition and subtraction, I add, subtract things, I get a vector. In cross product, I cross two vectors, I get a vector as my result, okay? Now, the second equation here, so I'm gonna say EQ2 here, this is our second equation. We're going to just talk about the magnitude of the resultant vector. So let's say I cross these two arbitrary vectors u and v. Notice the notation there with the little arrows above my variables here. That's the notation for a vector. Okay, so that's important just to keep everything readable when you're writing these things out. But notice what I'm saying here is I'm saying the magnitude of the cross product, okay? So this whole thing is a scalar. This is just gonna be a number, what I'm writing right now. So this is equal to the magnitude of u times the magnitude of v times the sine of the angle between them, okay? So this is just another really important formula to remember. Remember, this is just telling us about the magnitude of the cross product of u and v. It's not telling us what that vector actually is, just the magnitude of that vector, okay? So just keep that in mind. When you might use this, let's say I know the cross product, I know what u cross v is, I can find the magnitude of u and v, and there we go, now I can solve for the angle between them. So this is how you might be able to solve for the angle between two vectors. A lot of times we'll use a different formula, which we're about to go over now for that, but this is another option. So just keep that in mind, these two ways to compute cross product, okay? So that's it for cross product. Okay, well that's it for the math. Now we're gonna do a few examples, okay? So, example one. So, like I said before, cross product returns a vector that's perpendicular to the two vectors that I cross. So a perfect example then is to cross I hat and j hat. So naturally, what do you think I'm going to get when I cross I hat and j hat? Well, I'm going to get a vector that's perpendicular to I hat and j hat, which is k hat. So if we cross I hat and j hat, we should get k hat if cross product is doing what I claim it's doing, okay? So let's derive that third axis there using cross product. So we have this vector x and this vector y, they're perpendicular. And x is 1, 0, 0, or I hat. And this vector y that I defined is gonna be 0, 1, 0, or j hat. So now what happens, and I should use the correct notation here. So now what happens when I cross these two? Let's find out. So we're gonna do x hat cross y hat, okay? So let's write this out. So x is 1, 0, 0. So I'm just gonna do my preferred method. Feel free once again to practice the other method if you think that's easier for you, or if you just want more practice. So I'm gonna write out my x, and then I'm gonna repeat the first two terms to the right. Now I'm going to write y on the bottom, and I'm going to repeat the first two terms on the right. Okay? And then I'm going to circle my groups of 4, starting from the right and moving left. So I circle that group, and that group. And then I cross. Okay? So let's see what we get. So we're going to cross 0 times 0 is 0, minus 0 times 1, which is still 0. So we got 0 for that component. Then we're going to have 0 times 0, which is 0, minus 0 times 1, which is still 0. So once again, we have 0. Now we're going to do 1 times 1, which is 1, minus 0 times 0, which is still 1. So now we just have 0, 0, 1, which of course is the definition for k hat. So in fact, we see that when we cross these two vectors, we do get the vector that's perpendicular to them, and that's k hat. So hopefully now you can see really clearly what cross product is doing, mathematically speaking, okay? So now let's talk about what cross product is doing physically. So in this class, we're going to be talking about statics a little bit in a few studios from now. And one of the things we'll talk a lot about in that studio is this concept of a moment. So a moment, you can kind of think about it, it's sort of similar to torque. It's not exactly the same. There's a subtle difference between them, but it's basically just a rotational force acting upon a body, okay? So that's not super important. I don't want to get bogged down in that. What is important though is how do we compute cross product here? So I'm just going to tell you that the equation for a moment is r, this vector r, and we'll talk about what that is, cross with this vector f. Okay? So let's set up an example. So in my example, I'm going to have this wrench. So this is supposed to be a wrench, just to be clear. And then I've got a bolt right here. Okay, so there's my bolt. And I am going to exert a force, so this is F, so force of 50 newtons at the far end of the wrench. And the distance between the center of the bolt and that applied force is 20 centimeters. Okay? So now what I'm going to do is I'm going to set up my coordinate bases, my origin point right here. So this will be x and y. So now let's define all of our vectors. So f we already have. We can already see based on how I've defined my coordinate system that f is 50 newtons going in the y direction. So how can we specify f? F hat as a vector is just going to be 0, 50 is going positive. So that's 50, 0. That's it. So that's f. Okay, so that one's pretty straightforward. Now, r is always going to go from the point about which the moment is occurring. So the moment is occurring about this point right here on our bolt to the location where the force is applied. So from the point about which the moment is occurring to the point at which the force is applied, always in that order. So from the point at which the moment is occurring to the location of where the force is applied, that is r. So this is my vector r. And now we can figure out what r actually is. So you can see r is going in the negative x direction, and it's going 20 centimeters from the origin. Okay, so in that case, r hat is going to be, very simply, negative 20, 0, 0. There we go. Perfect. Okay, so now we've got r and f, so now we can compute the cross product, which is really what the whole point of this little problem is about. So first things first, what direction do we think the resulting moment is going to be in? Okay, so we have r, which is lying in the x direction entirely, and then we have x, which is lying in the y direction entirely. So if I cross these two things, I'm going to get a vector that's perpendicular to them. So we expect the result to be somewhere in k hat, and k hat alone, because that's the vector that's perpendicular to r and f, okay? So that's our expected result. We expect to get something in k hat. Let's see if that's the case. So we're doing r cross f in that order. Cross product is not commutative, so you cannot flip the order. If you flip the order, it'll change the sign, okay? So that's very important. It is R cross F, not F cross R. So this does not equal F cross R. It is not commutative, okay? So that's an important note there. Okay, so let's just keep on going here. So let's write out R. So -20, 0, 0. And then repeat the first two elements. And let's write out F. So we got 0, 50, 0. And then we repeat. And then we can circle our groups of 4. So there we go. Okay, so now we're gonna get 0 times 0, which is 0, minus 0 times 50, which is still 0. So we get a 0 there, which is what we expect. And then we get 0 times 0, which is 0, minus 0 times -20, which is still 0. So we get a 0 here, again, what we expect. And now we're gonna get -20 times 50, which is -1000, minus 0, because 0 times 0 is 0. And that's it. So now we do get something in k-hat. So our answer overall is going to be -1000 k-hat, and the units on that are Newton centimeters. And there we go. So that's all. So we get exactly what we expect. Now the other thing that's nice about cross product is that you can use this right hand rule, which I won't spend a lot of time on, but I do want to explain it briefly. So what you do is you take your index finger and you point that in the direction of your first vector that you're crossing. And then you're going to take these three fingers, you're going to point those in the direction of the second vector. So in this case, my index finger is F, and my second vector, or these three fingers, are going to be representing, this is R, and these three fingers are going to be representing F. Okay, so we've got R and then F. And make sure you use your right hand, and then your thumb is going to stick straight up, and that'll tell you which direction the resultant vector is going to be in. So if I'm looking at my image on the page here, I'm going to have R going this way in the negative x direction, and then F is going to be going this way. Well, my fingers are pointing the wrong way, so I need to flip my hand around. So now F is pointing in the right direction, R is pointing in the right direction, F is pointing in the right direction, and my thumb is pointing down, so that's negative. And look at that, our result was negative k-hat, -1000 k-hat, but it's going in the negative k-hat direction, so that's how you can use the right hand rule. So one more time, this is going to be R, that's the first direction, that's the first vector that I'm crossing. Then on the second vector that I'm crossing, in this case, it's going to be F. It's going to be these three fingers. I line those up depending on my problem. So in this case, I take my right hand, R, I point that this way. F needs to go this way, so I got to flip my hand around. So R is going this way, F's going that way, which is what we want. And my thumb's pointing down, so now I know that my result is going to be in the negative k-hat direction. Okay, so that is a quick note on the right hand rule. Okay, cool. So that's it for dot product. That's it for cross product. Now let's talk about dot product, okay? So dot product. Great. Okay, so first things first, we're gonna talk about the general formula. So let's write that out. So we've got A, B, and C. Dot, that's not multiplication. Once again, this is dot product. So we got dot, D, comma, E, comma, F. Okay? Great. Let me just make this a little bit more clear. There we go. Okay, so with dot product, I'm going to dot two vectors, and I'm going to get a scalar as a result. So this whole time I've been doing math operations on vectors. I've been doing those math operations, and I've been getting a vector as a result. This time is a little different. This time I'm going to get a scalar, just a magnitude as the result. So what we do is we multiply component-wise and add it together. So we're going to do A times D plus B times E plus C times F. Okay, so you'll notice this is just going to be some number. It's just a scalar in this case. Okay, so that is how you do dot product. Very simple operation. All right, now the second formula very similar in form to what we saw for cross product. So u dot v, for some arbitrary vectors, u and v, is going to be the magnitude of u times the magnitude of v times the cosine of the angle between them, okay? And notice this time I did not specify these absolute value bars around u dot v. And that's because I don't need to, because dot product is intrinsically already a scalar. So I don't need to specify that. This is already just a magnitude, okay? So those are our two formulas. This formula is probably more commonly used to find this angle theta. For the simple reason, the dot product is a little simpler to compute. You'll see, all I do is multiply the components and add them instead of this sort of seemingly very strange operation that is cross product. So this is a little bit easier. So a lot of times you'll see people use this. So now the other thing I want to talk about with dot product is that it's related to this concept of projection, okay? So now, this is not a super important point, so don't stress about it, but I think it is useful if you know what a projection is. If you don't, I'm about to explain it. So what a projection is, if I have a vector like this, okay? So that will be my vector, we'll call it A. And then I have another vector like this, we'll call it B. So now the projection, let's say I want to find the projection of vector A onto vector B. So what this means is, let's imagine for a moment here, let me move this down a little bit. Let's imagine that I have the sun above my vector right here. So right above my vector is the sun. So now the sun is shining down, directly down on these vectors, okay? So projection is kind of like the shadow that the sun makes. So it's like the shadow that vector A casts on vector B. That's kind of how you can think of projection. So what is that gonna look like, right? So now hopefully this is a little bit more intuitive. So our shadow is gonna end right at this dotted line, right? It's gonna go straight down 90 degrees right here, okay? And our resultant projection is going to be whatever this vector is, right? Right here in green, okay? So that will be our projection vector. Well, let's say I want to find the magnitude of that projection. Turns out dot product is helpful for that. So let's say I want to find the magnitude of this projection. So notice I have my magnitude specified here with my absolute value bars. In that case, I can do vector A, dot vector B here over the magnitude of vector B. And this will give me the projection, the magnitude of the projection of vector A onto vector B, okay? And now as it turns out, we can now plug in this formula right here. So let's do that and get sort of a simplified result, or just a different result. So let's plug in that formula. So A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them, which we already know, divided by the magnitude of B from before. So we can actually cross these two components out. So this whole thing is actually equal to the magnitude of A times the cosine of theta. Okay, so that's just another format. So this isn't a super important point, but it might help you visualize or intuitively understand, well, what's the point of dot product? Well, this is one point of having dot product, okay? So let's do a quick example problem, and then we'll get into MATLAB, okay? So example problem, let's say I have a vector A, which is gonna be 4, 8, 10, and I've got another vector B, which is 9, 2, 7. Okay, so if that's the case, I want to find A dot B and theta between them. So that's kind of my setup here, okay? So I want to find A dot B, and I want to find the angle theta between these two vectors. Okay, so let's do that. So first let's do A dot B, because that's the easy part. So A dot B, let's just compute that out. So let me zoom out a little bit so you can see everything. So let's just compute this. So it's going to be 4 times 9, right? Plus 8 times 2, plus 10 times 7. Okay? So if you do that all out, it's going to add up to 122. So that is A dot B. Okay, so that's the first result. So I'll highlight that one. Okay, so now let's find theta. So remember, we have this equation right here, and that's how we're going to find theta. So now we have this part of the equation, and we can easily find these two components, and then we can find theta because we know everything else. So let's do that. Okay, so we're going to have A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. And that is theta, which is what we want to find. So let's isolate theta. Okay, so if we isolate theta, we can see we're going to get A dot B divided by magnitude of A times magnitude of B. Okay, and all of this is going to be the argument for arc cosine. Okay, so this is theta. We've just isolated theta. So now let's plug in all of these values. So we've got inverse cosine, okay, and then up top we've already computed A dot B. It's right here, it's 122. So let's just write that on the top. And then we need to use our magnitude formula that we've talked about before. So that's just going to be for A, it's just going to be each component squared, added up, square root of all of that. Okay, so 4 squared plus 8 squared plus 10 squared. Okay, times, same deal. So the second component there, we've got 9 squared plus 2 squared plus 7 squared. Okay, and if you plug that into a calculator, you'll see that this is about 38.229 degrees. Okay, so that's theta. Okay, so that is it for the math content of this section. So now we're going to go over MATLAB. So let me line out the problems real quick, and then we'll hop over to MATLAB. So the first problem is these two vectors. We've got A and B. So the first vector is 1, 4, and the second vector is 3, 5, and we're just asked to compute a bunch of stuff in MATLAB, okay? So we've got the sum of A and B, we've got A minus B, we've got the magnitude of A and the magnitude of B, dot product of A and B, and then the angle between them. So this is all the stuff that we've been doing throughout this studio by hand. Now we're gonna learn how to do it in MATLAB. Okay, and then we've got another problem here, which is very similar to the first, except now our vectors are 3-dimensional, and we're additionally asked, now that 3-dimensional, to compute the cross product of A and B, okay? So that's all we're doing here. So let's jump over to MATLAB. So first things first, when you open MATLAB, it'll hopefully look something like this, okay? So you can see here, I've got a bunch of folders and stuff like that. That'll probably pop up for you as well. I'm just going to sort of move this stuff out of the way so we can get to the important stuff. And now I've got a blank screen. I also have a bunch of tabs here. But you may not, if you haven't been using MATLAB a lot and you haven't saved anything yet, you may not have that. So first things first, we're gonna go up to New, and we're gonna go to Live Script. Okay, so New, Live Script. Notice that I'm on the Editor panel, so if you don't see the option for New Live Script, go to Editor, and then New, Live Script, okay? And that should open up this file format that says .mlx at the top. So you'll see that .mlx, okay? That's how you know you're in the right place, okay? And if you ever kind of get stuck and MATLAB looks really crazy, you can always go to Home, Layout, and hit Default, and it'll reset everything. So I'm not gonna do that because it's gonna kind of mess with this, this recording. But just know that if your command window like disappears or something, you can always go home, layout, and just reset everything to the default. Okay, so I'm back in Live Editor now. As you can see, I just clicked on that. And so I'm just gonna go through the UI with you guys real quick, and then we'll start doing those example problems that I laid out just a few seconds ago. Okay, so basic UI, like I said, editor window here. We've got a run button, so we can, type stuff out, like, sum, I don't know, 3 plus 4. I can run that. You see I get something. So I've created a variable in MATLAB called sum, and I've stored a value in that variable, which is going to be whatever 3 plus 4 is. And you can see in it, when I hit run to the side here, it shows me that sum is equal to 7. Okay, so now if I put a semicolon here and I hit run, now I don't see anything. So what a semicolon does in MATLAB is it suppresses the output. Okay, so that's a really important thing to keep in mind. But if I write sum now, below this, we can see that it's going to store the value 7 in sum. So now sum, whenever I write sum, it's equal to 7, okay? So now I can also create different sections in MATLAB. So let's say I've written a bunch of stuff here, and now I want to separate it. So like maybe I have problems on a homework set or something like that. So I can go to section break. And now you can see I've created a new section. So let's say in this section, I'm gonna say difference, 3 minus 4. Okay, so this is pretty simple, but just to give you the idea. So now I can either press run. If I press run, it's gonna run everything. Or I can press run section. And if I press run section, it'll only run the section that I'm in. So you can see this is a section and this is a section. So just to illustrate this point, let me run just this section. And in fact, I'll get rid of this. But it'll still display because I'm not going to rerun that section. So let's run this section. See, it only runs this. So now if I run this, this goes away because I've suppressed the output. Okay? So this can actually be really useful. It might seem sort of useless right now, just like an organizational thing. But it's actually pretty useful because a lot of times you'll have a very long code. You might have some stuff that's kind of sort of computationally intensive, like a bunch of for loops or something like that, if you're iterating through a large data set or something. And so if you break things into sections and you can just run certain sections at a time instead of rerunning all of your code every time, it can actually save you a lot of time. Okay, so that's an important thing to note. Other good things to know, comments are right here. Comments in MATLAB are %. And so you can also highlight things and comment everything out. And then if you press the X, it'll get rid of the comments. You can also just type % and put comments in your code, okay? So that's how you do that. And remember comments, if you don't know, if you've never coded before, a comment is just something that's not gonna show up in your output. So it's just notes for yourself. So a lot of times if you have like a chunk of code that you don't wanna run, but maybe you don't wanna get rid of it yet. Let's say you change your code, but you're not super confident and you wanna keep your old stuff. A lot of times you'll just highlight all of it and comment it out and just leave it. And so that way it won't run. Other good uses for comments are, just organizational things so you remember what you're doing. So, if I forget, if sum is some super complicated function, I can say, sum returns 3 plus 4, and I won't see that when I run my code. Okay. So that's a quick rundown on MATLAB. The only other thing I want to say is if you go to home and you go to add-ons, this is where you can manage all your add-ons. You can download other things like the Symbolic Math Toolbox, which we'll be using in this class, which hopefully everyone's downloaded at this point. But if you haven't, you can do that here. You can also just type sim somewhere and run that. And if you don't have the Symbolic Math Toolbox, it'll throw you an error and it'll give you a link to go download it. So that's another way to do that. Okay. And yeah, and you can save your work here. And that's pretty much it. So at this point, what I'm going to do is I'm going to turn it over to myself, actually, from a few months ago, to finish out the MATLAB problems. So there's that. So let's start out with writing A. So I'm going to call my first vector A, just like it says in the problem. and it's 1, 4. So you can space vectors or arrays, same thing in programming world. You can space them with commas in MATLAB. That works. You can also just do a space, and let me take the semicolon off. So semicolon is how I suppress things, and I'll run that. So you can see the space works, and that pops out my vector. I like to use commas, but MATLAB can support a variety of different formats, is basically the main message here. If I wanted to do a matrix, then I could comma separate elements in each row, and then to create a new row, I might put a semicolon. Okay, so like this will create a new row, and then the columns are spaced with the commas. So if I run that, now you can see it creates a matrix. Okay, but for now, we're just gonna stick to vectors. Just a good thing to quickly point out, but not get stuck on. Okay, so that's how I create a vector. You can see if I put the semicolon on there, it suppresses the output so I don't see it. So that's really a good thing to do. Suppress everything that you don't need to see. Unless you want to verify that it's correct, then you can make that as an output temporarily. Okay, so let's move on and do B. So I can either write B on the same line or use a different line. Doesn't matter at all. I'm going to put a semicolon on that and keep it like that. So I'm going to put it on the same line. You can totally do it on 2 separate lines. It doesn't matter. MATLAB doesn't care about that. Okay, so the first thing we're asked to do is add vectors A and B. So to do that, I'm going to create a variable called sum, and then I'm going to delete it in a sec because it's actually not necessary, but I think it's instructive to point out, hey, this is how you do variable names in MATLAB. So sum equals A plus B. If I run this, then I can see that my resultant vector that I get from MATLAB is 4, 9. So you can see that it actually calls it sum. So now let's say I suppress this output, right, and I run that, nothing's going to show up. And if I write sum, then I run that, boom, it pops up with 4, 9. So I can see this variable sum now has stored this value. So this is how you assign values to variables in MATLAB, as we just saw really a second ago with A and B. So now that I've done that, you can also just write A plus B, but you're not storing that value anywhere. So that's not the most ideal thing to do. If you need to store the value, then give it a variable name. Okay, now I'm actually going to, well, I'll leave it for now. Leave this for now to keep this simple. Okay, so that's all great. So if I run that, that's fine. I'll get sum, and it's named, and it's clear. But maybe this isn't the nicest format. I don't think it is. Sometimes I want to write like literally A plus B equals and have MATLAB show me that as an output. And so you can do things like that, and I think that's a good thing to point out. You can make things look nicer, and I like to use this disp function, disp, for display. And the disp function basically takes in an array of strings. So we saw this array format earlier with the square brackets. We're going to do that again, except now we're going to do strings. So how do I specify that? I'm going to have these apostrophe signs, and then I can basically just write whatever I want in here and it'll pop up. And then it's just comma separated, and I can write the next string, whatever it is, and that'll pop up in my output. So in this case, I want to write something like A plus B equals, and then I want to display the actual result now. So the way to do that, so remember I said this is an array of strings that this function needs to take in, so we need to convert this numeric value in sum, we need to convert it to a string. So MATLAB has lots of built-in functions, and this is a good time to point out that if you don't know a function, you can always look up, just literally open up a Google window and type in, how do I do such and such thing in MATLAB? And MATLAB has great documentation with MathWorks. So it's actually pretty good, lots of examples. It's extensively used, so it's really easy to find out how to do things if you didn't know this function. But lots of built-in functions. So num to string is 1, so I can convert a numeric value to a string. So I'm going to pass in sum. And another thing that I do is I'll specify the precision that I want. So I'll put double and then pass in sum. So I have double and I pass in sum, which specifies the precision and data type that I have. because sometimes if you have some crazy number here, num to string will not be able to evaluate it. So this keeps that from happening. So I always just do num to string, double, and then whatever it is that I want to display. That's always the format that I use in this disk function. So that is all for that, and I can actually put a semicolon on this or not, doesn't matter. And I can run this, and I can see now I have this nice little thing that pops up, a plus b equals that. And I can get fancy with this. If I want to add the brackets back in here, then I can totally do that, and I can do something like this, whatever you want to do. I could even index some. So MATLAB is starts the arrays start with index 1, not index 0, which is a very important note. So I could do that, and I'm making this way too complicated, so I would not get into this sort of rabbit hole in the studio, but I just want to point out that you can make this as complicated and customize it however you want. So if I want to do something like that, I can make it look really nice. I can have the commas separated. Whatever you want to do is basically my point here. So you can make this as complicated or as simple as you want, but the disk function basically lets you customize very precisely how your output looks. And you can kind of see how I'm doing that. I'm just passing in the characters that I want, and it'll format it for me and pop out in the output. So that's the disk function. Another important thing to point out here, so we've learned how to index into arrays. So that first index will give me 1, and the second index is 4 in this case. Or I'm sorry, I'm looking at A. The first index is 4, and the second index is 9 for this sum variable. So we've learned that. We've also learned these two functions, double and num to string, and we've also learned that we can pass functions within other functions. So this double function is passed within is passed as an input into this num to string function. So you can sort of cast things and like that. Okay, so that's another sort of good thing to point out maybe. Okay, so now that I've done this problem basically just wants me to compute a bunch of other stuff. So I'll just copy and paste this disk, and I'm gonna make this a little simpler because this isn't super critical that it look super perfect like this. So we're gonna make this a little simpler. Go num to string. Boom, there we go. And this time I want to subtract a and b. So instead of having a whole variable dedicated to that, I'm just gonna do a minus b. So that'll kind of simplify this whole thing, and I can run that, and there we go. There's my answer. Okay. And of course you can make it look nice as I have the first one, whatever you want to do. I'm just going to keep it simple for now and kind of not get bogged down with some of that stuff. So the next thing it wants is the magnitude of A. So MATLAB actually has a built-in magnitude function. Of course you could write out the distance or magnitude formula, whatever you want to call it, in MATLAB and run it that way, but why do that when MATLAB has this nice function? So this function is norm, and that'll return the magnitude, and you can kind of pass that in to the double function, and yeah, that'll return the magnitude of A. So let's see that, and there we go. And then we're going to do the same thing for B. Here we go. Yeah, so we've got those things, and then the last part, it basically wants us to compute the dot product of A and B. So this isn't quite right, I'm using an asterisk, but hopefully it's, the main point is hopefully clear. This is supposed to be dot product, not multiplying. So we'll do dot is the function in MATLAB for dot product, and we'll do A comma B. So another good thing to point out here, so you can see I'm using this function dot in this case, and MATLAB is sort of popping up with a list of parameters that need to go into dot, and it also has some optional parameters. So the required parameters will be kind of bolded, and the optional parameters will be grayed out. So you can see it's mandatory that I put in these two vectors A and B, and then I've got some optional parameters, and I'm not sure what they do in this case, but you can certainly read the documentation and find that out. So right now, that's all I really want. There it is. A dot B is 23 in this case. So the last thing we want to find is the angle between vectors A and B. And so a really simple way to do this is just to use the equation that we derived earlier in the studio. But since we're trying to do this introduction to MATLAB, I'm going to do a little bit of a more complicated method and use the solve function. So we're actually just going to do sims, and we're going to set up a system with just one equation, and we're going to keep it really simple because it is just one equation, right? So our unknown variable is theta, so we're going to go sims theta. And then our one equation that we have in this case is A dot B. And this is just the equation that we mentioned before. And then double equals, very important, the second part. So it's going to be the magnitude of A times the magnitude of B times the cosine of the angle in between. And so now I personally want theta to be returned in degrees, so I'm going to write cosine D. So by default, cosine will be in radians, but if I write cos D, it will return in degrees. So I'm going to make that adjustment there. So now I'm going to say theta is equal to, so I'm setting the variable theta equal to this value, and I'm going to use VPA solve. Equivalently, you can use solve. I just want a nice simplified numeric answer, so VPA solve will give me that. That's the difference between VPA solve and solve. VPA solve is just numeric answers, and solve can return symbolic answers. So you could actually, if you had unknowns in this equation, like let's say this was times h, I could write h here, and I could actually solve for theta in terms of h. So MATLAB can do symbolic solving as well. Just use solve instead of VPA solve for that. So let's pass in. So equation 1, so you can see once again MATLAB is telling me what needs to be passed in, which is really convenient. So I've got the equation, and then my variable in this case is theta, and let's see what that returns actually. Okay, so there we go. So this is theta, and this is totally correct. I don't love this whole negative format. So basically what MATLAB has done, right, if I have a vector like this, MATLAB has gone all the way, long way around, so that's why it's got this huge negative number. I just wanted that little angle, so all I have to do is add 360. So we're just gonna do a little bit of post-processing work on this to clean it up. So that's a good thing to point out. MATLAB will not always give you answers in the format that you want. You might have to clean them up a little bit. So it's still good to have an intuitive sort of understanding of what's going on, because MATLAB can screw you up if you don't have an intuitive understanding. You kind of have to be able to check MATLAB, if that makes sense. So that's a good thing to point out, is just sort of make sure your answers make sense. So we're going to add 360 to clean this up a little bit, and there we go. So that's a much nicer answer for theta. Okay, so there's theta, and then for this question, it's not on the slide, but Andrew actually found this nice function quiver that I hadn't seen before. So this gives us a great opportunity to sort of plot some of these vectors and see how we graph things in MATLAB. So first thing when we're plotting things, we want to call figure, which just tells MATLAB that we're getting ready to create a new figure, whether that's a graph or whatever the case may be. So in this case, we're going to use this quiver function, and the way this quiver function works, it's not, it's a little bit strange, at least to me, and so I just looked up the documentation, and that's what anyone else would do as well if they didn't know, just like I didn't know what this function was. And so basically the first thing it wants is a starting point for your vector. So I want it to start at the origin, so I'm going to say 0, 0. And quiver, by the way, is only for 2D vectors. There's another function for 3D that we'll get to in a minute. So 0, 0, I want it to start at the origin, and then I need to provide the first index, the first value of my vector. So how do I do that? A, and then in parentheses 1 will give me the first index, or the value at the first index in A, and then A, and then in parentheses 2 will give me the value at the second index in A. So there we go, and then like I was saying before, so now we can see there's a lot of optional parameters. So the way this works with these functions is that, so this is the same for this quiver function, it's the same for plot, fplot. All of those is you specify what parameter and the optional parameters you're gonna provide a value for, and then you provide the value. So I want display name, and then my name that I'm displaying is, I'm gonna call this vector A. So that'll help us create a legend in a few minutes. And then I'm gonna specify another parameter, which is line width. And then the next thing I'll put in needs to be the value of line width, which in this case, I'm gonna say 2 to make it a little thicker and easier to see. Okay, and then I wanna plot the second vector, B, so I'm gonna call hold on, which is super important to plot multiple things on the same figure. So make sure to point that one out. And then I'm gonna call quiver again. So I'm just copying and pasting it. And we're just gonna modify for vector B to put that in there. Okay, so now to sort of clean up this graph and add some sort of different options, make this a little more interesting, we're gonna add an X and Y label. So you can do that with this X label function. So I'm gonna call this function, or this label X for X axis. And then we're gonna do a font size, and I'm gonna say 10. And of course, you can totally change all this stuff, but that is just sort of me playing around with it before recording this, and that looks good to me, so we're gonna stick with 10 for now. And then Y label, we're gonna pass in Y. And then we're also gonna give our figure a title. So I'm gonna call this 2D vector plot. And then we're gonna do font size again. And since this is the title, I'm gonna make it a little bit bigger. I'm gonna go 15 for this. Okay, so now we need to populate our legend. So the first thing to do is to get a reference to our axes, or our axis. And so the way to do that in MATLAB is to use this function get current axis, which is GCA, just stands for get current axis. And so we'll assign the current axis to this variable axis. Okay, and then legend, so we're gonna say legend1 is our variable that's referring to legend. Then we're gonna call legend, and we're gonna pass in axis, and we're gonna say show. Okay. And finally, we're gonna set some stuff with the legend. So we need a reference to the legend. So we're gonna say legend1. And now we're gonna have some different options. So a good thing to point out as well is if you have a bunch of parameters that you're passing into a function and it's starting to like run off the page, like let's say I had all of this stuff and then I had a bunch of more stuff and it's like getting super long, I can do this 3 dots and then enter, and that'll let me continue the function on a new line. So that's just a nice little thing to make your code look a little nicer. So since there's a bunch of stuff we're gonna put in here, I'm just gonna do that on this one. So I'm gonna say position, and I kind of pre-configured this. Of course, feel free to change these as you see fit, but these values gave what I thought was a good placement, so I'm gonna stick with these for now. And so I'm gonna go ... and provide my next parameter. And of course, the ... is totally optional. You don't have to do that. It just is another option to show students that you can do stuff like that. So I'm gonna say my font is italic, and last ... and our font size, I'm gonna go back to 10. Okay, so let's run that. There we go. So we've got a nice graph here. So the one thing that is a little bit irritating, at least to me, is that MATLAB will run your graph to the very edge of whatever line you're plotting. So you can see it's right at the edge of that, the tip of this vector. I don't love that, so I usually put some limits on this thing. So let's kind of add that in just to give me a little more space. So I'm gonna say X limit, and I'm gonna go maybe 0 to 4, looks good. And then I'm gonna specify a Y limit as well. And I'm gonna go 0 to 5. That looks good. So let's rerun this. And there we go. Now we have a little bit more space. So hopefully that gives students a lot of options in MATLAB. It provides sort of, hopefully what's a somewhat exciting introduction to the software, just to see, MATLAB could create really nice graphs and sort of do nice clean math for you. So hopefully it's really a tool to make your life easier is the idea. So next thing we're gonna do, there's another problem. This one's gonna go super fast because I'm really just gonna copy and paste everything from the first problem and then add on to it. So section break for the new problem. It's just a good housekeeping thing to do. And then before I do the new problem, well, let me just write a comment in here. So problem 2. So I'm gonna say clear vars so that we eliminate any references to like A and all of that stuff from the first problem above. And then I'm gonna say CLC clears my command window. I don't really need to do that, it's just sort of an option. And then you can also say close all for closing figures. Again, don't really need to do that in this case, but clear vars is a good thing to put in here probably. Okay, so now I'm actually gonna copy everything from here and I'm just gonna modify because this problem is pretty similar. It's just with the 3D vectors. And then we're gonna do a cross product thing as well. So should be super quick. So I'm just gonna modify A and B. And then I'm actually gonna eliminate this little sum thing. Don't have to do that. I'm just doing that to keep the format looking a little more consistent. So there we go. Okay, and then I'm gonna actually copy and paste this and we're gonna do cross product. So I'm gonna say A cross B is equal to, and in MATLAB, the function is cross. And you just pass in the two vectors just like we did for dot product. And that's pretty much it. So that should give me the cross product of those. And here we can run this section. And you can see it spits out all of this nice stuff. And now we just need to edit our graph. So instead of quiver, we're gonna do quiver 3 this time because we want to plot it in 3-dimensional space. So we're gonna add another 0 and we're gonna add our last component of A. We're gonna do the same thing with B. Remember to modify it to be quiver 3 and not just quiver. Okay, and there we go. And then we're gonna specify a Z limit, which I've already played with beforehand. So this looked good to me. Of course, you can change it as you see fit. And I'm gonna add a Z label. So I'm just gonna copy that and do Z label. Okay, so now I'm gonna run this section. And there we go. So now we get a nice 3D plot of these vectors. And that's pretty much it. So that's our quick introduction to MATLAB. Okay, great. So now that we've covered all the MATLAB content in this section, I just want to wrap up with a few helpful resources for you guys. So the first thing, the notes. If you don't know how to get to the notes, you can go to engine32.com/content, scroll all the way to the bottom. And hopefully that's how you're accessing this video as well. So hopefully you'll have figured that out by now, but there is notes for this. So I've written out all the MATLAB code and everything I've written basically in this video. So you can just go read it there as well in a much cleaner format, okay? So also this guide to Introduction to MATLAB and Syntax, you can click on that and look through that. That just gives you some helpful functions that you might be using in MATLAB. Also, I've included this guide that I wrote a few years ago when I was trying to prep some students in this class for Engine 40, which is the next class that you'll all be taking if you continue in the engineering track. And this is sort of more advanced MATLAB, so it's talking about things like for loops and data processing and if statements. These are all things that we will talk about later in this class, but you can kind of get a preview. Just look at it at your own discretion or don't look at it at all, because there is some content in there that might be a little bit confusing, because remember, this is the last thing that we did in this whole class. So yeah, just keep that in mind if you decide to look at that. Last thing, There's some commented out code from what we did in this studio today. And so you can access that right here at this link that says additional explanations for today's MATLAB questions. You can access the additional explanation and comments there, okay? And very last thing, just helpful resources. Here's some TAs that are good at MATLAB. That can help you if you have problems with MATLAB. These are probably the best TAs to go to. So yeah, feel free to ask any of us about MATLAB problems, questions, comments, how to do extra things, what you can use MATLAB for, whatever. Go to office hours, ask your studio leads, set up a meeting with somebody, whatever. We're here to help you guys. So let us know. And that's it for this studio. I know this video was kind of long. There was a lot to cover, but I hope this was helpful. So I'll see you guys on the next one. Thanks.